Hi and welcome to this iOS video on types in Objective-C. We're going to take a step back first and talk about types just in the C language that are inherited by Objective-C. Now, Objective-C is a strict superset, or what we call a strict superset of C. In other words, C is all still there. So if you're familiar with C, much of Objective-C is going to seem very familiar. Now, when we get into object allocations and things like that, and messaging, things are going to start looking pretty different. But at its heart, Objective-C is still C. So there's a lot of syntax that's borrowed from other languages like Smalltalk, predominantly. But Objective-C is really still C. So we're going to first look at the types, the scalar types that we get from C that Objective-C has. So the first thing I'm going to do is show you this little program, and all we're doing here is printing out the sizes of various types. So we're using the size of function to print these out. So I have a char and a short and an int. Now these are the three basic scalar types. There is also a long type. There is also a long type. But interestingly, when we see what the sizes of these are, and we'll run the program in a minute, we're going to see some interesting developments. Void is a type in Objective-C. So when we see void, it actually is a type. Of course, pointers are also types. So a void pointer will have a size, and we'll see that in a moment. In Objective-C, we actually have a Boolean type, and it is called bool, all capital letters. It's really the size of a car, which makes sense. It's a 1 or a 0, true, false, and we'll look at this in a little bit more detail in a moment. Floating point types, there are three. There is a float, a double, and a long double, and we'll print out those sizes here in a second. So I just want to print these out first and take a look at the output. So I'm going to comment out the rest of this little program. And we'll print those and take a look and see what we've got. So a char, and the values here are size ofs, so they're in bytes. A char is 1 byte, a short is 2, and int is 4. No surprises so far. Just remember, this is Objective-C is not really a cross-platform environment, so these numbers are going to be the same no matter what. So a char, a short, and an int all make sense here. A long is an 8-byte integer, and a long is also an 8-byte integer. So there's really no need to use a long because it's the same as a long. A void is a 1 byte value. A void pointer, and in fact all pointers in Objective-C, are 8 byte values. And a bool is a 1 byte value, so we printed those out. Now floats are 4 bytes, doubles are 8 bytes, and long doubles, unlike long longs, are actually 16 bytes. So a long double is a very large double precision value indeed. Okay, so we got those, and those all make sense. Now let's look at some of these true-false values, and we'll also look at unsigned here. Alright, so true and false are defined as true and false. In Objective-C, most oftenly we use yes and no, because these are actually defined as true and false, respectively. This is because, borrowing from Smalltalk, the value yes and no were used to represent our Boolean types. So we have a bool called a Boolean, and we've set it to equal to yes. And then we're just doing a printf with yes is the Boolean value, and no is not a Boolean, the not operator here. So not a Boolean will give us whatever not a Boolean is. Of course, we have unsigned types. We can qualify a type with the keyword unsigned. So I have an S car here, 0, and an unsigned car, U car, 0, and then I'm just printing out what happens when we subtract 1 from each of these. We have the pre-decrement and the post-decrement operator, of course, and the pre-increment and post-increment operator, and they work just like they do in C. Just a review, if we pre-decrement, it will do the decrement first and then copy that value. If we post-decrement, it will do the decrement after it copies the value. So if we put the minus minus here on the right-hand side of S car or U car, then we would get zeros in this printf statement. What we want is for the S car to show up as -1 and the U car to show up as 255. That proves that the U car really is an unsigned value. So let's go ahead and look at those. Okay, so we have what we just printed out. Yes is 1, no is 0. This is pretty typical of C. We don't really want to use Booleans as car values or as numerical values, but a yes is defined as being 1, and no is defined as being not yes. So just remember that. S car -1, a signed character -1, 0, is -1. An unsigned character -1 just rolls back to 255. All right. So far, so good. Now, let's, of course, in Objective-C, just like in C, we have car star strings. We've set up a character array here, a car star type, a string type, hello C string, and then we printed that out, and then we're going to print the object, or I'm sorry, I shouldn't say object yet. We're going to print the character at index 7 in that array. So when we have a car star, as we know, arrays are really just, even though it says it's a pointer to type character, it really is an array, and these syntaxes are interchangeable. An array, the name of an array is a pointer to the first piece of the array, the first item in the array, and a pointer can be used as a pointer to the first item in the array. So these syntaxes in C are interchangeable. So if we print the character at index 7, then we'll do it this way. We could also do this with pointer math, but this way is very much cleaner. So if we do this, when run this, we see here that we print out our car star, and then if we print out index 7 of the car array, we see that it's C. And we can count these 0, 1, 2, 3, 4, comma is 5, space is 6, C is 7. So there we go. Remember that in C, as in Objective-C, all arrays are 0 indexed. They're not indexed like with 1, as in Pascal, for example. Okay, so now Objective-C is an object-oriented language. So how are objects allocated? Well, we have a class called NSString. We're going to talk about objects and classes and things like that pretty much in our next session and beyond. But we have a class called NSString, and this is an objectified string, if you will. It's not a car star, but we can get a car star out of it. So here's an NSString named myString, and it is allocated as being equal to @hello world. Now, in Objective-C, this @ operator is very heavily overloaded. In this context, it means make an object out of whatever follows me. And in this case, it's saying make an object out of the string hello world. So the @ means make an object, and then we have hello world. So that is being copied into a new NSString called myString. But there's an error here. Why do you think that is? Well, it's because in Objective-C, all objects must be allocated on the heap. It tells us that an interface type cannot be statically allocated. So we're attempting to allocate an interface type. What's an interface type? An interface type is an object type. When we make a class, we have really two sections. We have the interface section and the implementation section. The interface section is what the compiler uses to classify, so to speak, that piece of code or make a class out of it. So it's telling us that a class type cannot be statically allocated. So it says fix it by inserting a star. And so in C terms, all objects are pointers, and we need to remember that. All objects are allocated on the heap. All scalars are allocated on the stack. So this is really C, isn't it? It's we're allocating an object on the heap. An object in Objective-C, a class in Objective-C, is kind of akin to a struct in C. So we would use the same sort of syntax to allocate a structure on the heap, or a structure type on the heap, right? And then we could get to that structure's various values. If that structure had contained pointers to functions, we could also execute those functions. And that's really what's going on under the hood here. Objective-C wraps some nice, easy syntax around a C struct that has members, data members, and also pointers to functions. And so that's really what's going on. So we allocate these objects on the heap. An string is a class type. We are allocating an object of that class type called myString, and we're copying the objectified string hello world into that new myString object. Then we print out, we can use a printf and use the message UTF string sent to myString, and that's the syntax here. We are sending the UTF-8 string message to myString, which is an NS string, which knows how to deal with this, and that will convert it to a C string. So we can actually printf as a string the UTF string value of myString, and that works. Or we can use the Objective-C function nslog, and if we do that, we have to print an objectified string for my format string, %at, this is the first overloading of this operator we've seen. This says format it, give me back the description of whatever I have, and then pass it myString, and we're cool. So we'll see two printouts. Hello world is the first one right here, and then the log statement actually prints out the date and time, and then the memory address within the types program, and then prints the string. So if we want all that stuff in the log statement, we can get that. If we want just a printf, we can get that, and this is how we do those. Very good. So what we talked about today is just some types, some very limited information so far on allocating objects on the heap and making objects out of classes. So in our next session, we're going to talk about making a class in and of itself. Now, one thing you might have noticed is that in this, we have used the Foundation framework. We've imported foundation.h, and that gives us an Objective-C environment in which to code. Another thing you may have noticed is that we have this @auto-release pool, and we're going to talk about this in upcoming sessions. But for now, auto-release pools are a way to make sure that all of these objects that are being allocated under the heap or onto the heap get released when the program ends. Objective-C is not a garbage collected environment. It is it is not garbage collected at all. It is reference counted. So when we allocate an object, it gets a reference count. When that reference count goes to 0, that object will be removed or freed in C lingo jargon. So remember, underneath the hood, Objective-C, when we create these objects out of classes, what's really going on is there's a malloc going on. So there's a memory allocation going on. If we don't free the object at the end, somehow, then that memory that was allocated will leak. So this auto-release pool is a way to make sure that objects get freed. Now, that's very much simplifying the issue, and we're going to talk about this much more as we go along. Okay, thank you very much.